I've been reminded that I should also mention that I'm vice chair of the IPN Special Interest Group and chapter of the Internet Society. While I do work at the Jet Propulsion Laboratory, I'm not here representing JPL, I'm not representing NASA, I'm not representing Caltech. But I do work there, and the work that I've been doing there for the last 18 years especially it very much informs the things I'm going to be talking about here. About 18 years ago, we started looking at something called delay-tolerant or disruption-tolerant networking. And the origin of all this was wanting to be able to extend the internet into outer space. And when we said that, people would say, oh, yeah, there was some amusement there. Oh, yeah, you're going to send emails to the warlords on Mars, right? You're going to be downloading videos from people on space stations. Well, who was there to talk to was not really the point. The objective of a network really is to automate communication that you can stitch it up by hand by dialing a phone or something. What the network does is make it automatic so that it scales up. So what we were doing was not extending the internet in the sense of being able to read the latest news of what Brad Pitt is doing. What we were aiming for was really Internet of Things. We were going to be talking to things in space. We were going to be talking to space probes. They were going to be talking to us. We knew from the beginning of the work on this delay-tolerant networking for interplanetary networking that the interplanetary network would be an Internet of Things. It was going to be that from the beginning, because there weren't going to be a lot of people out there for a long time. So a question that sort of then comes out of that is, what is the difference, Internet of Things? Why isn't that just the internet? And I will suggest that there is a qualitative difference here, because things are different from people. What we think of, what I think most people, most of the world thinks of as the internet is for communication among people. Things are different from people. Things don't have any sense of style, they don't have any sense of humor, they don't have any initiative, they don't have any curiosity, they don't get ideas, they don't have enthusiasms, they don't discover things that they want to explore and start doing research on. They're very, very patient. They're never bored. They're very fast. They have terrific memory. They have an entirely different set of expectations of information exchange from what people have. They will put up with a lot that people would not put up with, and they cannot tolerate some things, minor errors, omissions, oversights, that people just sort of fill in and compensate for. There are also going to be a lot more of them than us. There's a difference not only in the nature of communication, but in the scope of the communication, which really matters. The internet, as we typically think of it being used, is terrific for conversations, which is natural because it ultimately, it came from telephony. The first networks for exchange of information were telephone networks. We borrow a lot of legacy terminology from the telephone world. The telephone carriers were the earliest ISPs. People use it as a great big telephone system that sends a lot more stuff than just voice, although we use it for transmitting voice as well. We use it that way because people are naturally conversational. We talk to our friends, we surf the World Wide Web in an interactive sort of way, we browse online catalogs, magazines, we browse through libraries, and we navigate freely through all this data. When we click on a link and we want to follow it somewhere and it doesn't come back right away, we are annoyed. We are conversational. We expect responses to the things that we put into the system. Things do not care about conversing. Space probes, when they have information, they send it. That's pretty much it. If you have information for them, you send it to them, then they take it. That's pretty much it. There's not a lot of conversation there. There's no natural conversational element to the communication with a thing. A thing does not need to converse. When it has information, it wants to send it on. When you have information for it, it wants to receive it. Otherwise, it's busy doing whatever else it's doing. Things will ask for information at the moment they need it if that's the only way they can get the information. But that's not the way they really want to operate. This client-server structure that the internet, as we use it and as people expect it to operate, is a legacy of conversation. It's a legacy of the conversational architecture that is very natural to people and very alien to things. Things are more effective. They can respond more effectively. They can be more productive if they already know what they need to know at the time they need to operate on it. There's no need for them really to ask for information. You might as well just send it to them as soon as it's true. As soon as you know it, send them the information, and they can hold on to it because they have great memories, right? They'll just hold on to it for however long they need it. Conversational is natural for people. It offers no advantage to things, and that's a lucky thing for us because supporting conversations is expensive. Supporting conversations is expensive because the effectiveness of conversation varies inversely with the incidence of interruptions. Anybody here have a cell phone? If you have a cell phone, you probably are aware of this. If you have cell phone conversations that are breaking up, that are dropping, you're annoyed by this. It inhibits your ability to use the phone. Cell phone service providers compete on the basis of improving that capability, providing more reliable, more complete coverage, no breaking up, no dropped calls, no dead zones. Well, to do that, they have to build more cell towers. That costs money. The Internet of Things, if it were just the Internet and operated just the way the Internet, the way everybody expects it to operate, would be a very much larger fabric for conversations. The data access for the things, just as it is for people, would be conversational. We would do client-server. We would have web servers. We would have DNS servers. We would have things talking to servers whenever they needed something. And so any network outages would degrade data access. It would degrade the ability of the things to operate. This is key because a lot of important things, and we're going to be a lot of them, are mobile things. They're mobile entities, or they're in inaccessible locations. They're not going to be wired. There's not going to be many wired of these things. It's going to be radio transmission, and radio transmission is much more susceptible to disruption than wired communications. So you're going to have more infrastructure in order to improve the radio coverage, to minimize the network outages. And as the number of things in the Internet of Things increases and their geographic distribution increases, the scope of that infrastructure that's going to be needed to maintain that conversational communication fabric is going to be bigger and bigger and bigger and more expensive. And it's worse than that because as the number of things communicating increases, the amount of data that they're going to be sending increases. So what do you use how do you increase the amount of data that your transmissions can accommodate? You go to higher and higher communication bandwidths. You go to the K bands instead of X bands. You go to optical communication instead of radio communication. The higher the frequency of the medium you're using for transmission, the easier it is to disrupt it. The Ka bands are bothered by clouds. X band goes right through it. Ka band, no. Optical, it won't go through, right? You can't see through the clouds. All of which means that there's going to be spending a lot of money on infrastructure to sustain that conversational communication fabric. Security is just one layer of problem on top of that. The internet protocols are great for ensuring the confidentiality and the integrity of data that's being transmitted from one point to another. But suppose you've got a disruption in the network, or suppose you've got an interruption. Okay, the client is sending something to a server, or the server is sending something back to a client, and it can't go through. Well, okay, there are two things that can happen. You can drop the data, you can discard it, and then nothing happened. You have to try again later. Or we can hold on to it and send it on later, which is a great thing, except that now you're holding on to it. Now it's not in transmission, now it's residing in memory somewhere. And if it's residing in memory somewhere, it wants the same sort of integrity protection and confidentiality that it would have had when it was in transmission. Well, that means that the software that is retaining that data in memory somewhere while waiting for an opportunity to send it onward needs to do the same sort of integrity protection and confidentiality that the communication protocols are doing. Well, there isn't a standard for that. So the applications that have to hold on to the data and remember to send it again later on also have to remember to hold on to that data in a secure way. It's not an easy thing to do. These are not trivial software applications to build. Some of them will be done just great, and some of them might not. And there's an infinite variety of possible problems that can come out of this, and it all has to do with the fact that there are potential disruptions in the transmission, and therefore you have these problems. So the solution to that in part is cut down on the disruptions, and that's even more money. So what's the alternative? And I'll suggest that the alternative is something that we can take from interplanetary networking. When we started looking at interplanetary networking, we knew that round-trip times talking to our things could be very long and could be highly variable. The distance from Earth to Mars varies between 3 and 22 light minutes. So you have a round-trip time of up to 44 minutes. Quite different from round-trip times on Earth. But more than that, if the spacecraft you're talking to is an orbiter, well, it's going around a planet. So half the time it's on the other side of the planet. You can't talk to it. You have a network partition. You have periodic network partitions. The internet routing is not really comfortable with partitions. It generates new routing records, and then 20 minutes later, the partition is gone. What do you do about that? The thrashing to make the routing work could be so, there could be so much of it that by the time the corrections are made, the corrections are wrong. We knew then from the beginning that we would need protocols that didn't rely on the client-server model. We would need asynchronous communication protocols. The protocols would have to be what we started calling delay-tolerant. And shortly thereafter, we realized that protocols that did not rely on client-server architectures would be good for communicating when round-trip times were long for other kinds of reasons as well. Bursty radio interference, long delays while half of the conversation is going through a tunnel, signal attenuation because you're distant from the radio source. So these same protocols that were good for talking over very long signal propagation times were also good for talking over connections that were subject to disruption. They were disruption tolerant as well as delay tolerant, and which is, fortunately everything starts with D, so we just call it DTN and try to wave our arms and say, don't ask what the first letter means. The way DTN works, it's an overlay network architecture, which is very familiar to everybody here. It's the same as the internet architecture. In effect, it is the internet architecture one layer up. That is, the DTN bundle protocol, which is essentially the network protocol for the delay-tolerant networking architecture, is to IP as IP is to internet. And the DTN bundle protocol interconnects networks such as the internet and non-internet networks in the same way that the internet protocol interconnects local area networks. Forwarding at a DTN router is automatic, but it's not necessarily immediate because there may be disruption. There may be a period of time when you can't reach the other end of the connection. So there's instead of just store and forward where the data received at a router is stored in memory temporarily and forwarded right away, there's this notion of store and then hold on to it and carry it, possibly carry it physically for some period of time, and then forward it when you have an opportunity to do that. And because that is built in, what is also built in is confidentiality and integrity protection for data at rest, because the expectation from the beginning is that some portion of the time, the data that you are responsible as a router for getting to the other end of the network is going to be at rest, and it better be protected while it is. The reliability of transmission in the network depends on retransmission between relay points within the network, not end-to-end as in TCP, because if you've gotten the data halfway through a network round trip time of 80 minutes, and it breaks between a relay point and another relay point on the end-to-end path, you don't want to waste all that 20 minutes or 30 minutes of transmission you've already done waiting for it to be retransmitted from the source. You retransmit it from the point where you've lost it. And routing is different. The route computation takes into account not only the current topology of the network, but the future topology of the network, whether the future is scheduled and actually planned, as in space flight. We always have to plan flight mission communications, or just predicted based on analysis of historical contacts. Either way, the routing has to rely on its understanding of what the future topology is going to be, because by the time the data reaches a relay point, the current topology, the current connectivity will have changed. For those of us who are new to DTN, I'll just have a couple of slides here on sort of how it looks and how it works. This is a stack diagram that just basically shows the bundle protocol as a layer just above TCP in the internet portion of the end-to-end network, as an overlay network above the overlay. Not a particularly unfamiliar concept. The difference here is that there are little storage devices at each of the routers, because you may need to hold on to the data for a while because the connectivity to the next device may temporarily be interrupted. Just to give you an example of the operational benefit of this sort of general model of being able to tolerate disruption, the fact that DTN tolerates these disruptions within the end-to-end path means that end-to-end connectivity doesn't have to be contemporaneous in order for data to travel through the network. So in a case like this, here's, in order for data to get from S to D here, all of these contacts up until the last one were unusable because there was some portion of the end-to-end path that was busted. If you do it in a DTN sort of way, wherever you have an opportunity to send the data forward, even if it can't go through to the final destination, even if the end-to-end path is not supported, data still moves through the network, and so it arrives earlier, and the overall throughput can be higher. The current status of this work, as I said, we started looking at this about 18 years ago. There have been multiple demonstrations of the technology on satellite experiments, both in low Earth orbit and in deep space. There are DTN routers being stood up on the International Space Station right now. There have been a number of demonstrations and deployments of the same technology in terrestrial networks, a lot of them sponsored by the European N4C program. There are multiple open source implementations. The standards, the protocol specifications themselves are, of course, open. All of this work has been done originally in the context of the Internet Research Task Force, and so there are experimental RFCs dating back to 2007. But there's now a standards track DTN working group in IETF and we should be starting to publish standards track RFCs, I hope later this year. There's plenty of information about it if you want to learn more about DTN. This is a great website, thanks to Mike Snell. It's a terrific website that collects a lot of information on what DTN is and does. And the point I would like to offer here is I think DTN is a good fit for the Internet of Things for a number of reasons. It can provide the network service that things care about, and it can do it in a way that's a lot less expensive than building up a client-server communication fabric that would satisfy the needs of the gazillions of things that are going to be in the IoT. The standards are open, software is open source and proven. It's an affordable solution and a secure solution that scales up, which the Internet of Things is certainly going to need to do. And that's the end of my talk. Thank you very much.
Thank you very much, Mr. Burleigh. We'd like to open for questions.
So it's Vint, and I have to say I'm biased because I participated in some of this work too, so I'm excited about it. One obvious question is whether there are any current situations, like maybe on the International Space Station, where trying this idea out would make sense. The other thing that occurs to me is that we carry stuff around with us. And so you can imagine, going from one place to another, introducing exactly the disruption that you're describing. So if we imagine things that we have on our bodies or we carry with us that are disrupted in communication but want to be part of the IoT, then it seems like this would be a reasonable way to support that.
I completely agree. I think, in a sense, the case for DTN is easier to make in the context of things, because things are less demanding of their communication environment than people are. But for people as well, being able to get information late, but eventually, is a lot better than not being able to get it at all. And for communication environments where continuous conversational connectivity is difficult, DTN is a very useful, standardized kind of answer. I think the ability to, for example, provide emergency connectivity by hopping data between cell phones at an emergency site where infrastructure has been destroyed is potentially a very valuable capability that you get with DTN, and it's very difficult to get any other way. And there are plenty of other things to talk about there, absolutely. Any other questions, or time for lunch, I guess?
Thank you. Next question.
I have a question.
Oh.
Not a question, more a comment. So there are some real-life examples of experiments that have been done primarily by the N4C folks. Academics do a lot of work with DTN, but mostly on Earth, because it's really expensive to send stuff up to space. So like the Kars cave in Romania, right? So instead of pulling network cable, they wanted to monitor the air quality in this very deep cave system for two reasons. One, they had researchers that were going down deep into the recesses of the cave and doing work. They didn't want them to die. And they also made money by taking tourists through. So they had this, like mining railway system of transporting people, and they basically put a Wi-Fi enabled device running DTN on the car. And it went down, and there were Wi-Fi enabled data collection points that gathered air quality information. And when it got back up to the top, it updated the air quality data so they could get a trend, and they'd be able to identify if there was a human health concern. So that's a very practical example of using the permanent resident storage to enable this, what did you used to call it? Episcopal?
Epistolary.
Epistolary.
Epistolary communication, yeah.
Networking protocol.
Yeah.
So, if you have an Android phone, you can download a free suite of DTN applications developed by a university in Germany. They have a version that's very compact called IBR DTN. And you can get not so instant voice messaging, not so instant text messaging, and not so instant file transfer. And for many, many things, just as Scott said, they don't really care, how long it takes to get the data. So think of a situation like a farmer, it doesn't take that long, to get away from cell phone coverage, right? So he may want to collect soil quality information, so it'd be very, very cheap for him to just take his cell phone with him, that has Wi-Fi capability, and go pick up the digital mail from the sensors while he's doing work on the farm, bring it back to the house, and it drops off the digital mail. So there's lots of potential, what we call data mule applications for DTN that are potentially much, much more affordable. And one way of thinking about the issue that Scott was talking about the cost of architecture, infrastructure, just imagine in your mind a light pollution map of the globe. Most of the globe is dark. Doesn't have traditional internet infrastructure because that's where the light is. But there's lots of things that will be very, very valuable to get data from. Things we're monitoring air quality in the rainforest. Things that we're monitoring reindeer herders in Sweden. That's an actual use case. So I'm just saying, yay, Scott, great presentation. Thank you.
Thanks,
Yes.
Mike.
Thank you, Michael. Oh, sorry, you're going to
No,
respond?
just asking if there are any other questions.
Yes, I have a question. When Michael mentioned having you as a speaker, I was pretty excited about it, but then he said the word terrestrial, and my head started to hurt, and I'm wondering, oh my God, are we talking about space? How does that relate to this topic and us, technology as such? So, but he was able to break it down in a very understandable way. So my question to you, and your presentation also really helped crystallize that for me, because I'm not really technical, I'm on the business side of things, but work a lot in technology. So I was kind of able to connect the dots a little bit. How do you see the adoption of DTN happening? I know Michael touched a little bit on that, and who would be the main, target customers, especially in relation to Internet of Things? Thanks.
The infusion of this technology into spaceflight missions is underway sort of now. The Consultative Committee for Space Data Systems is adopting it as standard protocols for future flight missions. There will be an increasing number of missions that will be adopting it over the next few years. It happens kind of slowly because spacecraft are very expensive. The mission managers are very conservative. They won't use anything new that if they can avoid it. And new technology has to offer some very tangible benefit before they go for it. But that's slowly beginning to happen. Terrestrially, I think that the adoption of this technology, it may actually be the Internet of Things that is the forcing function for it because of cost more than anything else. I think that's the real driver. There are plenty of use cases that you can think of for communication, network communication technology that is extremely robust. But what we've been doing for the last 20, 30 years is whenever we come across one of those, we build a thing that fixes that solution. And there are lots of point solutions to these kinds of problems. And people have been content with that for a long time. Because each one of those things individually is small enough that you wouldn't make a large investment for it. I think it's what is, if anything, is going to infuse delay-tolerant networking into general use on the surface of Earth. I think it's going to be something that is a large enough problem that solving it once clearly offers some benefit to somebody. And I think IoT is a pretty good target for that.
Thank you very much, Scott Burleigh. I think he's helped us to get into a session where we are looking for a solution for some of the issues and challenges that we've been talking about since we started our meeting today. All right, so thank you.
Okay, thanks.